Next, we want to talk about how to convert a program into an efficient parallel program. In Chapter 3, Solihin identifies several steps in parallel programming, and you can see them in the diagram on the right. The first step is identifying parallel tasks. In a program that's iterating over a grid, a particular row of a grid might represent a task. In other words, iterating over a row might represent a task. Or if we have nested loops, maybe an inner loop would be a task. The next step is identifying variable scopes. That means determining which variables are private and which variables should be shared. Now, it's advantageous to make variables private if we can, because not only does that mean that they'll be accessed in local memory, but it also means we don't need to synchronize with other tasks in accessing the variables, so that enables the program to go faster. And then after that, we need to worry about task synchronization. As I said, if there are shared variables, the tasks may need to synchronize with each other, and in any event, we're going to have more than one task finish before we can go ahead with the next step of the programs. Now, the first couple of steps in changing a program into a parallel program is called task creation by Solihin, and it's sometimes also called task decomposition. The next step is grouping tasks into threads. Several factors need to be taken into account to do this. First of all, threads should not be too fine-grained. If the threads are too small, it's just not efficient to execute them because we need to create a memory map for a thread. That sometimes involves creating private data, and certainly it involves creating a process stack and initializing registers and so forth, so it's likely to be a few hundred instructions. And if the task that a thread is accomplishing is not substantially larger than that, it's just not efficient to use that size thread. Then there should be enough threads to make use of the processors. That means not only that the number of threads should be at least as many as the number of processors, but that means that we should have threads of varying sizes so that processors can stay utilized after their thread finishes, that they'll have other work to do, and we won't have lots of processors waiting idle in order for other processors to finish their work. And that really is the problem of load balancing. We should be able to balance the load so that processors can work with good efficiency. You don't want processors idle most of the time, as we saw in the last video. In addition to that, we have to talk about how to synchronize the threads. And in the last lecture, I think we talked a little bit of the need to have a couple of threads that are incrementing a variable. One does its read and then also its write before the second one does its read, or otherwise one of the increments will be lost. Solihin says that there are three levels of parallelism that we can concern ourselves with. First is the program level, and the quintessential example of that is a parallel compilation or a parallel make, where files are just compiled in parallel, and it's basically a different command for each file. So you have like on Linux, you have a different command for compiling each file, and they can be done in parallel because they run on different processors. There is no communication needed between them before they finish compiling their piece of code. Second, there's possibility for parallelism at the code level. We can look at how the code works, and we might be able to identify sections of code that can work in parallel. For example, if we're multiplying a matrix, we can have different tasks work on different parts of the result matrix, and they don't need to synchronize at all, and they can just run in parallel, and their work is pretty well balanced, so that's pretty effective. Sometimes, though, it's useful to change the algorithm, and I'm thinking of something like for sorting. A quick sort is a very efficient parallel sort because it's got lots of different tasks of varying size, and by just using a task queue, you can let a processor take the next task from that task queue when it finishes what it's working on. And as long as there's work to be done, there will still be work in the queue, so that can be used as an automatic load balancing mechanism. So even if you had a different kind of serial sorting algorithm in parallel, quicksort might be very efficient.